Resonance, that's going to be the topic of this last lesson in a chapter on molecular representation and resonance in my organic chemistry playlist. Now, this is my brand new organic chemistry playlist. I'm releasing lessons weekly throughout the 2020-21 school year, so if you don't want to miss one, subscribe to the channel, click the bell notifications. You'll be notified every time I put one of these up. This is something you learned back in Gen Chem, and resonance always implies that you've got delocalized electrons, and typically we're talking about delocalized pi electrons. Now, I want to bring this up in a context where you would have seen it in general chemistry, and then we'll kind of bring it to more of an organic chemistry focus. So back in the day, you guys might have made a Lewis structure for the nitrate ion. And if we draw a Lewis structure here, we'll find out there's 3 equivalent resonance structures. Now, we've got 5 valence electrons for nitrogen, so 6 each for 3 of the oxygens. 3 times 6 is 18, plus 5 is 23, and the negative sign gives us 1 extra electron for 24 total valence electrons. So nitrogen can make more bonds, less electronegative, so it goes in the middle. So we set up our skeleton and then fill up all the outside atoms. And so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. We've used all 24 now. We don't have any left over to give that central nitrogen. And the problem is nitrogen is definitely not happy. He's 2 electrons short of a filled octet, so somebody's going to have to share. Well, in this case, we've got 3 adjacent atoms that are all identical and all equally likely to share. And that was our evidence we were going to have resonance back in a general chemistry class. And in this case, because there's 3 atoms that can all share, so we're going to end up with 3 resonance structures. And because they're all identical atoms, they're going to be 3 equivalent resonance structures. So I could have it be the oxygen on the left that's going to do the sharing. That would leave us with this structure. I could have had it been the oxygen down below that did the sharing, or I could have had it been the oxygen on the right that did the sharing and got the double bond there. And give me a sec just to get my lone pairs in. All right. We also want to put some formal charges on here. In every single one of these, the nitrogen has a positive formal charge. So 5 is a normal valence, minus 1, 2, 3, 4 lines is plus 1. Whereas the oxygens that have a double bond are neutral. Oxygen's normal number of valence electrons is 6, minus 1, 2, 3, 4, 5, 6, minus the dots and lines is 0. But for the oxygens with single bonds, it's 6 minus 1, 2, 3, 4, 5, 6, 7, and you get a negative 1 formal charge for all those oxygens, again, with a single bond in any one of these structures. Okay, so there's our nitrate ion. If you add up those formal charges, you'll see that overall this ion has a negative charge. And these would be called 3 equivalent resonance structures. Now again, we said that resonance always implies delocalized electrons. What that really means is that electrons are in multiple locations at the same time, something that we don't experience in any sense at the macro level, but at the atomic level or the molecular level, it's totally possible. And so these resonance structures, we should know, are just tools. They don't actually exist. It's not like these are oscillating back and forth. That's not what that double arrow means. And just a quick word to the wise, that double arrow is different than this double arrow. You can't use this one for resonance. This is your resonance double arrow. This double arrow means equilibrium. Just a quick aside. But these double arrows don't mean these are oscillating back and forth. These structures, none of these actually exist. So they're just a tool that we use to figure out what the real structure, molecular ion, is going to look like. And we call that real structure the resonance hybrid here. And in this case, I can see that I've got a double bond in this location in this structure, but a single bond in the other two. So there is a partial bond here. And in the same light, there's a partial bond here and a partial bond here as well. Now, the nitrogen's got a positive formal charge in all 3 structures, so we're going to give it a positive formal charge. But each oxygen is neutral in at least one of the structures, but negative in at least one as well. And so all the oxygens are going to be partially negative. Cool. And again, we call this the resonance hybrid. And it's a better representation of what the real molecule looks like. All right. And so in this case, you can kind of see that we've got 1, 2, 3, 4 bonds total. So shared in 1, 2, 3 locations. And so we'd kind of think of this as equivalent as a 4/3 bond, a 1 1/3 bond. So that's stronger than a single bond, shorter than a single bond, but weaker than a double bond, longer than a double bond. That's the kind of the way this works. Cool, but that's 1 extra pi bond shared in all 3 locations at the same time. And so it's an extra third of a bond. So that's what we mean by delocalized electrons. That pi bond is in multiple locations at the same time. Now in OChem, we like to focus on how you get from one resonance structure to the next, because we're not going to be just drawing basic Lewis structures like this. You're typically going to be given one resonance structure and then have to predict all the possible resonance structures instead. So instead of starting by drawing some simplistic Lewis structure, we're going to be giving you probably more complex organic molecules, giving you one structure and say draw the rest. And so you're not going to arrive at these resonance structures in the same way we did in general chemistry. And so we've got some rules for you for what electrons you're allowed to move to get from one resonance structure to the next. And so it turns out you're allowed to move non-bonding electrons, first off. So non-bonding electrons can move to any adjacent bond, but that's it. And then pi electrons. And pi electrons are allowed to go to two places. So if you got a pi bond, it can move to either adjacent atom, like this pi bond right here that you see in double or triple bonds, could move to either adjacent atom, or potentially it could go to an adjacent bond as well. So you got two options with those pi electrons. So, but those are the only electrons you can move, either non-bonding electrons or pi electrons, and we move them in such a way to get to the next resonance structure. So, well, it turns out to go from this structure to this one, so I can see that in this case that I'm going to have a double bond right here, but that oxygen on the bottom has 3 lone pairs. Now it's only got 2 lone pairs. One of those lone pairs must move. Well, the only place lone pairs are allowed to move is into an adjacent bond. So there must be where that pi bond is coming from. Okay. So, but I can also see that this pi bond right here is gone in the next structure. And so where does it go? Well, I'll go from 2 lone pairs on this oxygen to 3 lone pairs on this oxygen, and now we know where it goes. And so in this case, it implies that these 2 electrons move to this adjacent atom. Now again, in principle, pi electrons have options of moving to an adjacent atom or to an adjacent bond, but I can see to get from this structure to this structure, if I already have this tron, that's where they must have gone. Now, one thing to note, arrows here, so we've got a full-headed arrow, we said, or a double-headed arrow. So because we'll see in a little bit that you can also have a single-headed arrow, and double-headed arrows show the movement of 2 electrons. This will be important for all of the rest of your 2 semesters of OChem. In mechanisms, we like to show where the electrons are going to make bonds and break bonds and things of this sort. And when you show a double-headed arrow, you're showing the movement of 2 electrons at a time, whereas when you've got a single-headed arrow, you're going to show the movement of 1 electron at a time. All right, so, but these 2 arrows get me to this resonance structure. And then to get from this one to this one, we do the same kind of thing and say, okay, where are the electrons moving? Well, in this case, I can see that we're going to end up with a double bond here and only 2 lone pairs on the oxygen. And so, yet again, one of these lone pairs must be forming the pi bond we see in the next structure. But also I go from double bond to single bond, so these pi electrons need to move. And where do they go? Well, we go from 2 lone pairs on oxygen to 3 lone pairs on oxygen, so they must be forming another lone pair on that oxygen. Cool, so when we're drawing resonance structures, we like to go sequentially from one to the next, and we typically show the arrow pushing of how we get there. Now here, we had already drawn all these by drawing, kind of the standard way we draw Lewis structures. But again, from an organic chemistry perspective, you're going to have just one of these pictured here, and you're going to have to figure out, based on patterns, how it is you actually get to the next one based on predicting the arrows, and then based on where you've predicted arrows, then you'll be predicting the structure. So we've kind of done this backwards, but you'll see what I mean very soon. So now we're going to get into drawing some resonance structures, and you'll find out that we typically learn how to draw resonance structures for 3 different kinds of compounds. And it turns out when we draw resonance structures, you're going to have electrons in multiple locations, and that lowers the energy of those electrons because they're seeing multiple nuclei and stuff like that, and they're attracted to those. So it also often spreads charges around, and charges get shared on multiple atoms, like we saw in nitrate, where there was a partial negative charge on 3 different oxygens, a negative charge being shared between 3 different oxygens. So at least it was actually 2 negative charges being shared between 3 different oxygens. So that spreads out that charge. That also makes things more stable. And so we often talk about the idea of resonance stabilization. It makes things more stable. And typically the more resonant structures, the more stable. So, but you also got to pay attention to like where you put negative charges. Generally you want a negative charge on a more electronegative atom and a positive charge on a less electronegative atom, things of that sort. All right, so there's 3 main structures we can undergo resonance with and resonance stabilization with, and carbocations are one of them. That's carbon with a positive formal charge. Lone pairs of electrons, and here I've got a carbanion, which is pretty common to show up, but it technically doesn't actually have to be carbon or an anion for that matter. So it could be a neutral nitrogen or neutral oxygen or something like that. So we'll find out some different situations where we stabilize lone pairs, and then radicals, where you have a single unpaired electron. That is your third example of where we're going to do resonance stabilization. Now, a couple terms I want to introduce you to, and they're the terms allylic and benzylic. So, and if you've got the study guide in front of you, they're already on your handout there. So, but allylic means you are one bond away from an alkene. So one bond away from an alkene. So an alkene, carbon-carbon double bond, we learned in the last lesson. And if you're exactly one bond away, so this carbon right here, I'll highlight with the C, and this carbon right here, they're both exactly one sigma bond away from our double bond right here. And therefore they get the term allylic. And the reason they get that term, so it's a special term, is because if on one of those allylic carbons that we've labeled, it has either a positive formal charge, a lone pair, or a radical, it will have resonance. So got another term as well, and this is benzylic, and benzylic is very similar, but it means you're one bond away from a benzene ring instead. And so one sigma bond from a benzene ring, that is the benzylic carbon. We'll label him as well. And means the same thing though. If you have a positive formal charge there, a carbocation, or a lone pair like a carbanion, or a radical at that location exactly, there will be resonance with the pi electrons in the benzene ring. And we can actually make it a bigger generalization. So if you are a carbocation or a lone pair of electrons or a radical, so but note that both these could be termed as non-bonding electrons. So if you're a carbocation or non-bonding electrons, and you're exactly one bond away from pi electrons, which includes both allylic and benzylic and others. So, but if you're exactly one bond away from pi electrons, there will be resonance stabilization. So that's where these terms get significance in this chapter. So because again, if you have a carbocation or non-bonding electrons in an allylic or benzylic position, there will be resonance. Cool, and we're going to use that to kind of predict when we should see resonance. So we'll start with carbocations here, and let me make some room for drawing all our resonance structures here. So, but we're going to kind of parallel these, but it turns out how we approach drawing resonance structure and the arrows we draw for the movement of electrons are going to be different in these three classes. And so that's why we're going to present them kind of in the same breath here, in the same on the same board in parallel with each other so you can see the difference. So carbocations are the easiest, and so we'll start there. And so in this case, this positive formal charge is 2 bonds away from these pi electrons. There will be no resonance involving those pi electrons at all. Cool. But this carbocation positive charge, 1 bond away from these pi electrons, there's going to be resonance. And so this guy's a carbocation because he's only got 3 bonds. So if you look at this, he's got 2 bonds to carbon atoms showing. That implies that if there were no formal charge, he'd have 2 hydrogen atoms bonded to him as well. But with a positive formal charge, it means he's only got 3 bonds total. So he actually only has 1 hydrogen. And so he's got no filled octet. He's really unstable when he doesn't have a filled octet here. And so our goal is to get him another bond. And that is possible when he's exactly 1 bond away from pi electrons. And so, and this is 90% of the time, if you're going to stabilize a carbocation, it's because you're 1 bond away from pi electrons. Now with pi electrons, we have options. We could move these pi electrons to either adjacent atom. I could move them over here, or I could move them over here, and that would put a lone pair either on this atom or this atom. In fact, if I did the arrow on the left, the arrow on the right first, it would put a lone pair and a negative charge on that carbon and leave behind a positive formal charge on that carbon since he'd be missing a bond now too. So, and then this positive charge would still be there as well. That'd be a horrible idea. So most of the time you don't want to add additional charges into your resonance structures. We'll see one exception for the most part, but most of the time that's true. So same thing would happen if you move the pi bond to make a lone pair on the atom on the left here. There'd be a negative charge and a lone pair on that atom, and then a positive formal charge left behind on this atom, and then we'd still have a positive formal charge on the carbon we've begun with. Neither one of those would help us. Our goal is to make him more stable, and we make him more stable if we get him his 4th bond. And so we won't consider either of those options. Technically, you know, pi electrons are allowed to move to an adjacent atom, but if it serves a purpose. In those cases, it wouldn't serve us a good purpose here. But if we move these to the adjacent bond, it's totally going to serve us a purpose. By moving them to form a double bond in this location, that carbon's going to pick up his 4th bond and no longer have a positive formal charge. So let's draw that next resonance structure here. All right, so this one hasn't moved, but this one has now moved to this location. And if you take a look then, this carbon, which still again had 1 hydrogen to begin with, still has 1 hydrogen, but now has 1, 2, 3, and then the bond of the hydrogen be the 4th bond. Now it has 4 bonds. No longer has a positive formal charge. However, one of the carbons did lose a bond in the process and will now have a positive formal charge, and that is this one right here, 2 carbons away. Now you might be like, well, why isn't the next one to him? Well, this carbon here has the pi bond on his right, and then here has the pi bond on his left. And whether it's on his right or on his left, he's good. He's like, I have 4 bonds no matter how you slice it. But it's this carbon right here that used to have this pi bond in this structure and now no longer does. And so he only has 3 bonds now. He's now got the positive formal charge. He's now the carbocation in that structure. Cool, so that's our first resonance structure we can draw. And then you got to ask yourself a question in the case of carbocation is he allylic or benzylic to any additional pi bonds? So now he's definitely going to be allylic from the one we just came from. He's going to be 1 bond away from the pi electrons we just moved. So that's always the case. And moving them back just gets you back to the structure you came from. But is he 1 bond away from any additional pi electrons? And in this case, he's exactly 1 sigma bond away from those pi electrons. And so we should anticipate more resonance. And so here we can also move these over to that bonding position. And again, we could consider moving them to either adjacent atom. It's just not going to help us stabilize this carbocation in this case, so we'll not consider those. But if we move it to the adjacent bond, we will indeed get a new structure here that gets this carbon 4 bonds and will make it not a carbocation. So it will lead to stabilization here. All right, so we've got that there, and now we've got these here. And now indeed this carbon right here picked up its 4th bond, is no longer a carbocation, but 2 carbons away, that's a pattern here, we now have a carbon that is missing a bond and is now our carbocation. And he's not 1 bond away from any additional, pi electrons. He's always going to, again, be 1 bond away from the pi electrons we just moved to get to this structure, but he's not 1 bond away from any additional structures, which means we are now out of resonance structures. And there we go. Cool, so these are our corresponding resonance structures. And we can draw analogous structures if you're stabilizing a lone pair. Notice I made it pretty much identical structures, except we have a carbocation here versus a lone pair of electrons here. So, and pretty much you're going to get analogous structures here. So let's just go down the list and make the corresponding structures. So we're going to have the pi bonds in all the same locations we have the carbocation, and instead of a cation here, we're going to have the lone pair and the anion there. And same thing on the last one. And it actually works exactly the same way with the radical. So we're going to get the exact same analogous structures. So, but instead of a cation or instead of a lone pair, we'll just have a single electron there. Cool. Now the reason we went through and drew the structures first on this one is I wanted to show you that it is just as easy to predict the resonance structures when stabilizing lone pairs or radicals as it is with the carbocation. But the arrow pushing of the electrons is more challenging. And so if you know what to expect for what the structure should look like, it'll make the arrow pushing a little easier. And so the truth is, if you learn how to push arrows, it'll make predicting structures easier. But if you can predict the structures, it'll make learning the arrow pushing easier, and they'll feed into each other. All right, so we started with the easy one with carbocations. The question is, how do we get now from this structure to this one when stabilizing a lone pair of electrons? Well, a lot of students look at this and they just look at where things need to go and they're like, oh, I see this. Yeah, we just need to move this bond to right there, and then we can move this lone pair over to here. And life is good, beautiful, except that totally violates our rules for how we're allowed to move electrons. So if you recall, lone pairs, the only place they're allowed to go is to an adjacent bond. They are not allowed to jump even to the next atom over, let alone 2 atoms away over to this one. So this would definitely not get us our movement of electrons we want. It looks like it should get you the right structure. It's just totally a violation of what electrons can do in drawing resonance structures. And so what's actually going on is, since this lone pair is not present on that atom in the next structure, these actually have to move, but the only place they can go is to an adjacent bond, either here or here. Well, it turns out they can't go here because you can never move them towards an sp3 hybridized atom. And the reason you can't is it would give it a 5th bond and it would violate the octet rule. So that's the 3rd rule in moving electrons. You can't move towards an sp3, and it just means you're going to violate the octet rule if you do. So, but we could move them towards an sp2 over here, which is what we're going to have to do. We're going to have to form a pi bond there. We can't move them all the way to the next atom, but I can move them towards that atom by forming a pi bond here, and there indeed is that pi bond in that next structure. Now the problem is if that's the only thing I do, we're going to have a double bond here and a double bond here, and this carbon would still have a hydrogen and would have 5 bonds and violate the octet rule. So it can't be the only thing we do. And so in this case, I see this next structure that there is no pi bond in this location. So, and I need to get a lone pair. Well, there's an easy solution then. We're going to move this to that atom, and put the lone pair on that carbon. And so when you're stabilizing a lone pair, typically most of the time your resonance structures to get from one to the next is not going to involve just a single arrow, a movement of 2 electrons, but 2 arrows of movement of 4 electrons. And typically you get this pattern. You're going to have a lone pair become a pi bond and a pi bond become a lone pair. So the lone pair becomes the pi bond and the pi bond becomes the lone pair. That's almost always how it works. All right, so we go to the next one and we're going to have the same kind of pattern. So our lone pair is going to become this pi bond and the pi bond is going to become this lone pair. And there's our movement of electrons. So for stabilizing lone pairs. So typically, again, most of the time it's going to involve moving 2 sets of arrows at a time. So 4 electrons moving from one to the next. Now radicals are just plain unique. So they're different than either one of these, and they're the most confusing of the 3. And oftentimes, professors will even leave this out at this stage. So maybe half the time or so. So half of you guys, this will be relevant, half it won't. And if it's not, I'm sorry, but it will be more relevant later on in the semester, even if it's not right now. So the way this works here is this electron right here, the only place he's allowed to go, being a non-bonding electron, is to the adjacent bond. But problem is, so first off, I can only move that one electron. And since I'm only moving one electron, it's only a half-headed arrow. Okay, well then where's the other half of this pi bond come from, and where's that radical come from? Well, it comes from the fact that this pi bond here is actually going to split in half and move in opposite directions. So the other half of the pi bond comes from one of these, electrons from the old pi bond moving to where the new one is, and then the other electron moves to the other side to form the radical on that carbon as well. And so when 2 electrons in a bond move in opposite directions like this, we call this homolytic cleavage. Not the most important word now, but it'll be relevant later, and we'll have a whole chapter on radicals typically at the end of first semester. So, but that's how the movement of electrons works, and it's very unique, definitely distinct between these 3. So, but a lot of students will learn resonance, they won't realize that, arrow pushing, we call it arrow pushing, in carbocations versus lone pairs versus radicals is different. And they don't realize there's 3 distinct cases they gotta know, and it's just a big jumble in their heads, and that's why I'm taking the time to kind of spell it out in all 3 parallel paths. So let's go to this last one here. We'll use the radical to make half of a pi bond, and then we'll split the pi bond up to make the other half of the new pi bond, and to make the radical in the last structure as well. Cool, and this is kind of your normal arrow pushing. Now, with resonance structures, we also got something else to identify that's pretty common in organic molecules. Now, in the nitrate ion we just showed, we had 3 equivalent resonance structures. They were all equal. They all contributed equally to what the resonance hybrid would look like. But that doesn't always happen in typical organic molecules. And so the way it works, when you've got multiple resonance structures, if any of those structures are more stable than the others, then the resonance hybrid is going to look more like that structure than the rest. So if we look at this, we've got to know some trends on stability then. So for carbocations, there's some trends on stability, and the trends on stability go from tertiary to secondary to primary. So let's write that up here. So we'll do it in a different color to highlight it. So tertiary is more stable than secondaries, more stable than primaries, more stable than methyl, if we cared. And so if we look at this, we've identified these carbocations. So this one's secondary. It's a carbon bonded directly to 2 other carbons. This one is also secondary. It's bonded to 2 other carbons. But this one over here is primary. And so if we draw that overall resonance hybrid here, so we can see that we've got delocalization going on all through there, and we're going to have a partial positive charge here, here, and here for that resonance hybrid. All right, now it turns out all 3 of these carbons, though, are not going to be sharing that partial positive equally, because all 3 of these structures don't contribute equally to this resonance hybrid. And the way this works, since these 2 carbocations being secondary are more stable than this one over here that's primary, we would refer to these 2 structures as being major resonance contributors. And that means that the resonance hybrid is going to look more like them, and then this guy would be a minor resonance contributor, which means that the resonance hybrid looks less like him. And so what we can conclude is that there's more partial positive on these 2 carbons than there is on this carbon here. So most of the time it's going to work out that you usually have just 1 major and then 1 or more minors, but this one actually had 2 major resonance contributors. Now for the carbanions actually follow an opposite trend in stability. So a carbocation here is electron deficient. It doesn't have enough electrons, and it turns out when it's bonded to carbon atoms, so they have a way of donating electrons towards it, which make it less positive and more stable. And so being bonded to more carbons when you're electron deficient makes you more stable. But in the carbanion's case, he's not electron deficient. He has too many electrons, as evidenced by having a negative formal charge. And having too many electrons, if there's carbons next to him that are giving him even more electron density, that's actually going to make him less stable. And so the trend is flip-flopped here. And so for carbanions, we're going to have methyl, and I'll symbolize that by Me here instead of CH3. It means the same thing, but it's more stable than primary, it's more stable than secondary, it's more stable than tertiary. And once again, this is a secondary carbanion in this structure, secondary in this structure, primary in this structure. And so now all of a sudden, for carbanions, it's the primary that's going to be more stable than the secondary, and that's going to make this the major resonance contributor, and both of these minor. Cool, and what that means is in the overall resonance hybrid, where once again we have delocalization of pi electrons all through those regions, a localized pi bond right there, and now instead of partial positives we have partial negatives. So, but now since this is the major resonance contributor, we see that we're going to have more negative on that primary carbon on the far right, more partial negative charge there than on the two secondary carbons. Cool. So finally we'll look at the radical as well, and for radicals, so these don't have a formal charge, but they are electron deficient in the fact that they don't have a filled octet. And being electron deficient, just like with carbocations, they want to be bonded to as many carbons as possible. And so they follow the same trend. Tertiary is more stable than secondary, is more stable than primary, is more stable than methyl. And so in this case, again, we've got a secondary radical here, secondary radical here, primary radical there. And so once again, the secondaries are more stable, so these would now be the major resonance contributors, and this guy the minor. Cool. Not usually as important something to kind of diagram out for radicals, but definitely for cations and lone pair stabilization at this stage. And once again, half of you guys probably won't even see resonance with radicals just yet, but it will show up before the end of the semester, I promise. All right, so we just want to work a couple more examples. There's a couple other things we need to show, and one involving carbocations and then one involving stabilizing lone pairs. So for this one here, we've got a carbocation, so we definitely want to stabilize that and get him his fourth bond if possible. And the first question we should ask ourselves is he one bond away from pi electrons? And indeed, he is exactly one sigma bond away from these pi electrons, and we should totally expect resonance. So we'll move these over to the adjacent bond like we do to stabilize carbocations typically. And our next structure, cool, so we got him as fourth bond, and just like the trend follows, 2 atoms over is now the atom missing a bond, and he has a positive charge. And so then we normally ask ourselves, well, is he one bond away from any additional pi electrons? And no. The only pi electrons in that molecule are these guys, at least from the outside of the look of it. But for carbocations, there is one other way to stabilize them and get another resonance structure. And again, 90% of the time, 9 times out of 10, it'll be about being one bond away from pi electrons. But the second case is, do any of your adjacent atoms have lone pairs? Because lone pairs can be moved to an adjacent bond, which means I could use this lone pair to form a double bond from oxygen, which would give him a fourth bond, or I could use this lone pair to form a pi bond there, form a double bond with nitrogen, which would also get him his fourth bond, and that's your other scenario. So again, 9 times out of 10, resonance comes down to being one bond away from pi electrons. The other 10% is, are you a carbocation next to an atom with lone pairs? Cool. And in this case, we got 2 options. So we're just going to pick one of them. I'm going to pick the nitrogen first. And you might think my reasoning is that, you know, oxygen's more electronegative, and so he holds on to his electrons more, so maybe nitrogen we should consider first. We'll do both, essentially, but we will find out that nitrogen will be better at sharing than oxygen, being less electronegative. All right, so next structure we'll draw then. It's going to have a double bond to the nitrogen. Cool, and that's going to leave the positive formal charge now on the nitrogen. It might be easier to see if I actually draw in those hydrogens. So normal number of valence for nitrogen is 5, minus 1, 2, 3, 4 lines is plus 1. Cool. Now, we're there, but we also could have done this sharing from the oxygen. So let's do this in a different color. We also could have said, well, what if oxygen did the sharing? And maybe we might be inclined to like branch it off right here. So, and if we look, the structure we'd get would have the double bond with the oxygen. So the last resonance structure we might have arrived at, had we branched it off there differently, would have a double bond now to the oxygen. And that would leave a positive formal charge on the oxygen. Oxygen's normal valence is, number of valence electrons is 6, minus 1, 2, 3 lines and 2 dots. 6 minus 5 is plus 1. All right, and that is the last resonance structure. However, there's a temptation to try and get there from here. And a lot of students will try and do this. They'll put another double arrow right here and just branch it off in the middle, 2 different directions. And they'll draw this last resonance structure over here. Turns out you're not allowed to do that. For proper resonance, you have to have a linear, continuous chain of resonance structures. And so to get to this last resonance structure, what you're going to have to do, because since we can't branch off, it violates the rules, so is we're going to have to undo the one we just made. So from here, I need to get it back to here by undoing this arrow. And so we're going to take those electrons and move them back onto the nitrogen. That way, we can move the electrons in and have the oxygen being the one forming the double bond. Cool. And so in this case, we actually had to move 2 sets of arrows, but that's only because we had to satisfy the rule of having a linear progression of resonance structures here. So, but there are all our resonance structures. So we saw that something new here, that you can get resonance for a carbocation if he's next to an atom with lone pairs. But we'll see one other thing new here. In the last example, we had all carbocations in our resonance structures, but now we also have a nitrogen cation and an oxygen cation. And the question now we have to say is major versus minor. Who's the most stable resonance contributor? All right, so for a positive charge, it's opposite of negative charge. Negative charge, you typically want to put it on the most electronegative atom, period. For a positive charge, you typically want to put it on the least electronegative atom, but not period. So all things being equal, you want to put it on the least electronegative atom. And so in this case, you're like, well, carbon, carbon, nitrogen, oxygen, the least electronegative is carbon. Done. Okay, it's going to be one of these. And he's secondary, and we'll figure out what he is. And, you know, however, you have to say all things equal. And all things are not equal here. So turns out that when you have a positive formal charge on carbon, you only have 3 bonds on each of these carbons and no filled octet. Whereas when you've got a positive formal charge on nitrogen, you've got a filled octet. When you've got a positive formal charge on oxygen, you've got a filled octet. And so having a filled octet, much more stable than not having a filled octet. And so in this case, actually, these 2 resonance structures are better than when the positive charge was on the less electronegative atom, which seems counterintuitive. You could also look at this one other way. If you notice, the number of pi bonds in this structure is 1. And there's 1, 2, 3 lone pairs. And in this structure, you got 1 pi bond and 3 lone pairs. But in this structure, you've got 2 pi bonds and only 2 lone pairs. In this structure, same thing. You've got 2 pi bonds and only 1, and then I should draw the other end, and only 2 lone pairs. And so electrons are more stable, lower energy when they're bonding than when they're non-bonding. And since these 2 structures have more electrons that are now pi bonds and less that are non-bonding lone pairs, you could look at them as being more stable that way. So whether you look at it from the octet rule perspective or from the number of bonding electrons perspective, these are more stable resonance structures than these 2, even though the positive charge are on more electronegative atoms like nitrogen and oxygen. Now between these 2, all things are equal. They have the same number of pi bonds, same number of lone pairs, and everybody's got a filled octet. And so now between these 2, you would say I'd rather have the positive charge on the less electronegative atom. And so picking nitrogen would be your choice because nitrogen's less electronegative than oxygen. So this guy's going to be our major resonance contributor. This guy would be minor, and these guys even more minor. But we don't really usually kind of rank them. We just say 1 major usually and a bunch of minors. So unlike that first example where we actually had 2 majors and 1 minor, but most time it's usually 1 major and a bunch of minors. Cool, and that just means that the resonance hybrid, even though the positive charge is going to be shared on 2 carbons, a nitrogen and an oxygen, more of that partial positive charge on the resonance hybrid will be on the nitrogen than on the carbons or the oxygen. All right, let's look at one more example with lone pairs. And in this case, we've got this lovely carbanon. We want to stabilize that. And in this case, we have to ask ourselves the question, is it 1 bond away from pi electrons? And in this case, yep, it's totally 1 bond away from pi electrons. And so we should expect resonance, and we're going to form a pi bond. So lone pair becomes a pi bond becomes a lone pair. Now, a lot of students ask me and be like, Chad, hey, why didn't you just move these over to the adjacent bond over here and then move these up here? Well, we could, but we'd miss some of our resonance structures, and we'd miss the fact that some of that electron density is going to be on this carbon right here. If we just skip that resonance structure, we'd miss that. And so that's why the pattern goes lone pair becomes a pi bond becomes a lone pair, is you want to consider moving it, if possible, to the adjacent atom before you move it further to the adjacent bond, or you might miss some of your resonance structures. So let's get that resonance structure up here. Now we'll ask ourselves the question, is this one bond away from any additional pi electrons? Well, yeah, we're one sigma bond away from these pi electrons. And so we could then, lone pair becomes a pi bond becomes a lone pair. And I forgot a couple of my lone pairs. Let's just get those on. And draw one more resonance structure. Cool, and that'll be our last resonance structure. We're not one bond away from any other pi electrons at this point, except the ones we just moved to get there. So there's our resonance structures. We have a negative charge on a carbon here, and an oxygen here. And here we don't have to worry about like that whole all things being equal and stuff. With a negative charge, put it on the most electronegative atom, done. And so the one on oxygen here, negative formal charge on oxygen, is definitely our major resonance contributor, whereas these other two with the negative charge on carbon will be minor contributors. And again, that means that the resonance hybrid is going to have more partial negative charge on the oxygen than on either one of these carbon atoms. So last thing in this lesson, we've got to talk about a connection between resonance and hybridization. And we can see a slight contradiction that arises when we start trying to figure out what's the hybridization of a particular atom. And if you judge that based on a single resonance structure, you might not get the right answer. So one thing to remind, so in this case, we've got a couple of different resonance structures, and just recall that these resonance structures don't exist. The real molecule is an average of the two, and again, we call it the resonance hybrid. So we've got a partial negative charge here and a partial negative charge here. And so if I ask you, hey, what's the hybridization of that carbon atom right there? You should not think of what is it in this exact resonance structure, because this structure doesn't exist. You should think about what would it look like in the context of the actual molecule which the resonance hybrid depicts. And so if you look at this, it might be helpful if I draw in some hydrogen atoms. So we've got a couple on that carbon, and we've also got couple on that atom. Same thing here, got one here and here, and here and here. So if you look at this carbon on the left here, and I said, what's his hybridization? You'd look and you'd say, well, he's bonded to 3 atoms and no lone pairs. That's 3 electron domains total, and so he's going to be sp2. Problem is that we look at that same carbon atom in the next resonance structure, and here you say, oh, wait a minute, he's bonded to 1, 2, 3 atoms and has a lone pair. That's 4 total domains, and so maybe he's sp3? And so the question is, what is he? Well, again, the key is that neither one of these resonance structures even exists. So what actually exists is an average of the two at the same time. So we're like, well, then is he sp2.5, Chad? Well, no. No such thing as sp2.5, or at least nothing we're going to consider in this class. So the question then becomes, which is a more accurate reflection of the real structure? Well, if we take a look at what's going on here, you guys might recall with carbon's 4 valent electrons. So he promotes one from the s into the p, so he's got 4 unpaired electrons. And then we've got an option. If he's going to be sp3 hybridized, then he's going to mix the s's and p's, all 4 of them, to make 4 brand new sp3 hybrids. Or if he decides to be sp2 hybridized, he'll only mix one of the s with only 2 of the p's, making only 3 hybrid orbitals, and that third 2p orbital will just be left unhybridized. And the key is this: if you have a leftover unhybridized p orbital, you've got it so that you can make a pi bond. And so if you're sp3 hybridized, you don't have an unhybridized p orbital, and you can't have any pi bonding. And so unhybridized p orbitals are the only thing that can be used for pi bonding in this class. So if we look at that and we say, okay, so looking back again at that carbon, is he involved in pi bonding? Well, in this structure, I'd say yes. And in this structure, I'd say no. But the key is, again, we shouldn't be evaluating these structures. We should be looking at the resonance hybrid. And in this case, he does have a partial pi bond. It's not a full pi bond, it's a partial pi bond. But if I said, is he involved in pi bonding? You'd have to say yes. You could not say no. And if he's involved in pi bonding, then he cannot be sp3. sp3s are never involved in pi bonding. And so as a result, he must be sp2. And so this is the connection between resonance and hybridization. If you look at just one resonance structure, like if I looked at this one, I'd get it wrong. And if I looked at this one, I might have just by default got it right. So, but the truth is I should be looking at the resonance hybrid, realizing, it can't be sp3, has to be the sp2. Usually the way it works out is if you have in one structure it's sp2 and one it's sp3, it's just going to be sp2. That's usually the way it ends up working out. Let's look at a couple of examples. All right, so the examples we're going to look at are two different nitrogen atoms on the same molecule. We want to give both their hybridizations. And if we didn't know anything about resonance and its potential connection to hybridization, we might just look at this and be like, nitrogen's bonded to 1, 2, 3 atoms, has a lone pair, sp3. So, okay. And look at this one, same thing. So bonded to 3 atoms, lone pair, 4 total domains, sp3. Problem is then we'll say, okay, well, now that we do know about hybridization, if either of these is involved in resonance, then it's going to have delocalized pi bonding going on, and having partial pi bonding, it can't be sp3, it would have to be sp2 instead. And so the question is, are either one of these lone pairs involved in resonance? And recall that lone pairs are involved in resonance if they're exactly one sigma bond away from pi electrons. So this guy here, is he 1 bond away from pi electrons? Well, he is 1 sigma, 2 sigma bonds away from pi electrons, no resonance. So he really is sp3. Nothing new there. But this lone pair right here on the nitrogen is exactly 1 sigma bond away from these pi electrons. There's going to be resonance here. We could draw another resonance structure where we'd have a double bond right here, which means there's really a partial double bond right here, and this nitrogen cannot be sp3. He must be sp2 instead. And so that's kind of the approach we take in looking at resonance hybridization. If you have a situation where there's no resonance that's possible, well, then it's exactly how you'd see it in the structure you have. But if resonance is possible, you might have to consider that other resonance structure. And in this case, I never drew it out. Didn't really have to. I just realized this guy couldn't have been sp3. But we could have moved lone pair into a pi bond into a lone pair. And having a double bond there, I could envision that that nitrogen would have been sp2 in that structure. So in this case, again, because of resonance, it just couldn't be sp3. Had to be sp2 instead. Cool. If you got something out of this lesson, please consider giving me a like and a share. And if you're looking for practice problems or the study guides that go with this, check out my premium course on chadsprep.com.